All right, this is kind of the mother of bringing electrochemistry, thermodynamic favorability, thermodynamics, and Gibbs free energy, and equilibrium all together. So we're going to cover the first two topics here in this short video. All right, so thermodynamically favored redox reactions are those which have an electrical cell potential that is greater than 0. So those are thermodynamically favored when the standard cell potential is greater than 0. So we're using the same equation that we were using yesterday to figure out what the cell potential is under standard conditions. So once again, if something is thermodynamically favored in one direction, it will not be thermodynamically favored in the other direction. All right, so this formula and the table of standard reduction potentials can be used instead of an activity series, which we haven't gone over. Activity series is a list of substances from top to bottom that will react with those that are below it. And I'm not even going to introduce it because we don't need it. But the standard reduction potentials can be used to determine if any of the redox reactions are thermodynamically favored. So we've already learned how to use this from the standard reduction potentials. So the question is the following reaction thermodynamically favored? Okay, we have barium sulfate, aqueous barium sulfate and lead reacts to form barium solid and a lead sulfate solid. And in the solution, here are our half reactions. And because this is actually the balanced chemical equation, we're not figuring out we're not changing the sign of this. We have to change the sign of, since this is not actually being reduced, but lead is being oxidized, then we have to change the sign here. So this is a non-thermodynamically favored process. Now, how can we relate that to Gibbs free energy? Well, Gibbs free energy is how we figure out whether something is thermodynamically favored from a heat and entropy standpoint, but we can also look at that from a potential energy standpoint, which is the electrical cell potential. So the number of Gibbs free energy is equal to the negative number of moles of electrons that are transferred from a balanced chemical equation. So N has typically stood for moles for us, and it still does here, but now it's moles of electrons. F is the Faraday's constant, which will relate the charge per moles of electrons. So this is given to you on the AP exam, Faraday's constant. So is the Gibbs free energy equation in relation to the electromotive force, okay, or the cell potential. So as delta G becomes more negative, the standard cell potential, the electromotive force, becomes more positive. And the opposite of all is also true. So find delta G and the equilibrium constant for the following reaction. So here is our reaction. The reduction of the chromium ion and the oxidation of manganese. Okay, so we have 6 electrons that are transferred in total here. So first we need to find the reduction potential from the values before. So we will flip the sign of the reduction half reaction for manganese because it is oxidized here. And we're left with a positive electromotive force, which is thermodynamically favored. So we should be able to predict our sign for delta G now. What do you think the sign for delta G is? Yes, negative. Okay, so to find out how many electrons were transferred, we have to look at the half reactions. Okay, so the reduction of chromate, 2 moles of chromium ion and 3 moles of manganese. There's 6 moles of electrons that are transferred here. Okay, so we plug in -6 times the Faraday's constant multiplied by the electromotive force, and this needs to be in joules per coulomb for the electromotive force, but Gibbs free energy is often expressed in kilojoules, so we can just change that value. But just include all of your units all the time. So include coulombs per mole of electrons. Include moles of electrons, joules per coulomb, so that we can cancel out our coulombs and we're left with joules per mole. So it's important that you're using your units all the way through. Next, let's find the equilibrium constant. Okay, so we can use delta G is equal to the negative gas constant R times temperature times the natural log of the equilibrium constant. So we can use this equation, which is given to us. We have everything we need. We have delta G. We have our gas constant, the negative gas constant, and we are, this is the 8.314 joules per mole times Kelvin. We're going to use that because that will allow us the units, all units, to cancel. We're using Kelvin here because those are the standard state, and we can rearrange very, very carefully and solve for the equilibrium constant. So ask yourself, does this equilibrium lie far to the left or far to the right? You nailed it. It lies very far to the right. All right. Now, a cell can only remain under standard conditions for a brief moment in time. So as the reaction proceeds, the reactants are consumed, the products are formed, and in doing so, the concentrations or partial pressures of the reactants decrease, and the partial pressures or the concentrations of the products increase. And this causes the voltage to decrease. So anytime we have concentrations of reactants or products that are not at 1 molar, or partial pressures that are not at 1 atmosphere, or temperatures not at 25, then we have non-standard conditions. Okay? So as the reaction proceeds, the cell potential, the voltage decreases as the concentration of the reactants decrease and the concentration of the products increases. So we can apply this quantitatively. So this will decrease until the voltage is 0. So when the voltage is 0, the system is now at equilibrium and the cell is dead, or a dead battery. Okay? So let's look at this equation right here. Copper is oxidized and silver is reduced. Okay? Thermodynamically favored process. Now we can look at this from Le Chatelier's principle. If the system is originally under standard conditions and silver ion is added, we're adding reactants, will shift the reaction to the right, then the rate of the forward reaction increases, the voltage increases, electron flow increases. Okay, so that's if we move this way, then everything here increases. But if we remove silver ion, the reaction will move this direction and the rate decreases, voltage decreases, and the electron flow decreases. Now let's look at it from the product side. If we add a product, the reaction shifts to the left and everything decreases. If we remove a product, things shift to the right and everything increases. Okay, so this is just applying Le Chatelier's principle to the electromotive force under non-standard conditions. So let's do a little quantitative analysis of this. If a cell, originally under standard conditions and functioning according to the equation below, gold is oxidized when silver is reduced. Gold is reduced, silver is oxidized. So if we were asked to find the gold ion concentration according to, if we have a concentration of zinc ion that is above the standard conditions, well, we can relate that amount at which it is above the standard conditions. So 0.14 here comes from the 0.14 here, and we can multiply that by the rate, by the mole ratio in the balanced chemical equation, and then we can subtract that from the standard conditions, and this will be our concentration. So this is an important one to think about here. Okay, this is not the concentration. This is the change in the concentration of the gold ion. Okay, that's it for now.